Hello, Professor. My name is Joshua Rodriguez. My lab partner is Carlos Verdosca, who has helped me on this project a lot. And today, I'll be presenting CCS Rinka 46, Project 1, which is an advanced traffic light controller. So as you can see here, these are all the ports I decided to use. PB5, PB4, and PB3 are all connected to red, yellow, and green east to west LEDs respectively. I decided to implement positive logic for this as I tried to implement using negative logic as a state in the project. However, no matter how hard I tried to implement it, it was unable to function properly because one of the LEDs refused to turn on. So I decided to instead use positive logic. I also have PB2, PB1, and PB0 being connected to the red, yellow, and green north-south LEDs. These are also using positive logic. I also have the north-south sensor being connected to PA3 and the east-west sensor being connected to PA2, both of them using positive logic. Finally, I also have the north-south right turn sensor being connected to PF4, and this is the only port that decides to use negative logic, or I decide to use negative logic with. I also have red right turn connected to PF1 and green right turn being connected to PF3, both of them using positive logic. As you can see here, I also decided to have two include statements. The first one being systic.hex, which is essentially gonna act as a file that's gonna help implement our delays for the LEDs. Also, we have the pll.hex file, which is essentially gonna also be used for the simulation. It's gonna help us switch between the states for the simulation. So as you see here, we have many defined ports. However, the ones you want to take note of is light port B and light port F, which is essentially gonna take the outputs from the finite state machines and use them to correctly make sure that the LEDs for both the north-south traffic and the east-west traffic are correctly implemented. So that it makes sure these ports basically make sure that they're either green, yellow, or red for a specific time. Or for a specific state, I should say. Also, the other two you should keep in mind is sensor port F and sensor port A, which is essentially going to receive inputs, and based on those inputs, it'll determine what state the finite state machine will be. I also have two free implemented from my system clock, and this makes sense as we're going to implement using port A, port B, and port F. So as you can see down here, we also have our struct state machine, and the only differences being from the other lab is that we have turn and traffic, and also, which are going to be used for our finite state machine. Also, we have the number inside next is 8 rather than 4, and the reason for this is that in this finite state machine, we're receiving 8 inputs rather than 4. And for this state machine, we also have 6 different states. The first one being go W, which essentially means green light for the east-west traffic. The wait W, which is the yellow light for the east-west traffic. The go S, representing the green light for the north-south traffic. The wait S being the yellow light for the north-south traffic. The go SRT, which is the green light for both the right turn signal and the north-south traffic. And the wait SRT, essentially meaning the yellow light for the right turn signal and the north-south traffic. And this also shows how it's going to be changing from the different states. So as you can see here, we also have our initialized statements for PL and systic, and we also have our system clock set to 2 free, which is going to be up for A, B, and F. And as you can see here, we also have these many different initialized functions or statements here, basically doing the obvious things like disabling the analog function and clearing the bits, setting up the inputs and outputs, ensuring that there are no alternate functions, and enabling some pull-up resistors and digital pins. As you can see down here, which is the final part, we set our initial statement or our first state for the finite state machine to be go W, which is our first state. As you can see here, we can see that light port F and light port F are receiving outputs from the finite state machine being traffic and turn. Essentially, what this is going to do is going to make sure that it will correctly lit up the LEDs in the proper form. So like at one point, like one of the LEDs will obviously be green while the other being red. Also, we have our 6-tick wait 1S, which is essentially going to act as a delay for the lab. It's going to wait for 1 second, which is what it should be doing, as Winia waits several seconds before the LED should turn colors. Also, we have sensor port A and sensor port F reading reading the sensors. Essentially, they're gonna read the inputs from the lab so that it is properly able to. So depending on the state, it'll determine what color the LED should be depending on the state, and it'll also determine what the next state is depending on the inputs, and that'll be our S equals FSMS next dot input. So let's start off first by doing the simulation. So we just go to here and we build it up and go to debug. So as you can see here, oh wait, hold up, I need to bring up the analysis window. There we go. So as you can see here, all we need to do is start it right there and set our switch to 1. So let me pull out for you, or zoom it out for you. So as you can see here, we could see that the east-west traffic is currently red, while the north-south traffic is currently in red, which makes sense since that is our first state. And if we were to continue going on here, the states will obviously never change. However, if we do want them to change, we'll simply click on PA3 down here. And essentially that is the north-south sensor. So what this does is that it's going to change the state. So as you can see here, the east-west traffic is going from green to yellow to red. And the north-south traffic is going from red to green. As you can see here, this continues going, unless if we want to switch traffics once again, we'll click on PA2, which is essentially going to be the switch that controls the east-west traffic. So if we were to continue going to states, as you can see here, the LEDs will obviously switch colors. And when both of them are on, it'll obviously continue switching from the states. So it'll go from, one of them will go from green, yellow to red, and the other one will go from red to green. And this will continue on to show that they are switching from the states, which is what it should be, as the traffics, if both of the buttons are on, then the traffic should switch, always. Unfortunately, I was not able to figure out how to properly implement the button on the microcontroller, the right turn signal, and that is the only thing I was unable to do for the logic analyzer. So now let's head to the demo. So as you can see here, we just need to switch the sources, options for target. We go to debugger and we go here to use the microcontroller. We save and we build. And then now we go to our lab, and then we click on here to turn it on, and then we program the device. So as you can see here, both of the switches are currently turned off, so that is why there is no switch between the LEDs. Obviously, as you can see here, the east-west traffic is staying in green, while the north-south is staying at red. However, when we click on one of these, this is the east-west, since it's connected to PA2, and this is the north-south. So if we were to click on here, it would obviously switch from the states. However, for whatever reason, even if one of the switches is turned on, it'll seemingly always switch from the states, even if it's just the north-south sensor being on. So essentially this would work if both of the sensors were on, both for east-west and north-south. However, it doesn't seem to be the case here, as even if one of the switches is on, then it will just continuously switch from the LEDs. Me and my partner tried to figure out what the problem was for this problem for this specific demo. However, despite all of our searching, we were unable to find a solution. So I believe that is all. So thank you, Professor, for looking at my lab, and I hope you have a wonderful day. Goodbye.